Welcome to the Network Plus Prepcast, your dedicated audio companion for mastering every objective on the CompTIA Network Plus certification exam. This series is produced by baremetalcyber.com. Name resolution and time synchronization are two of the most foundational services in any network, and also two of the most deceptively complex to troubleshoot. While issues with DNS and NTP may not immediately present as obvious failures, they often manifest as broken applications, failed logins, inaccurate logs, or general system instability. In fact, some of the most confusing support cases stem from a simple misconfigured DNS address or an NTP client that's several minutes out of sync. Because both services operate silently in the background, their failures are often mistaken for application or network errors. In this episode, we focus on troubleshooting failures in DNS validation domain name system and NTP network time protocol. These services underpin nearly every function of a connected environment, including browsing, authentication, logging, and encryption. We'll explore the typical symptoms, misconfigurations, and diagnostic tools used to isolate problems with name and time resolution. Whether you're preparing for the Network Plus exam or supporting real-world systems, knowing how to identify and fix these subtle but critical services will save you time and improve reliability. Let's begin with DNS. At its core, DNS resolves domain names to IP addresses. Anytime you visit a website, send an email, access a cloud service, or even run a system update, DNS is at work translating host names into routable addresses. Applications don't use domain names, they use IPs, and DNS bridges that gap. If DNS is unavailable or returning incorrect data, almost every network-dependent function breaks, even though the underlying connectivity might still be perfectly healthy. Symptoms of DNS failure often appear as strange and inconsistent issues. A user may report that a website is unreachable, but if they ping the site's IP address directly, it works fine. Applications may hang, time out, or crash because they can't resolve host names. Even basic commands like ping or telnet might fail, not because the server is down, but because the name can't be resolved. Long connection delays often result from timeouts while waiting for DNS fallback or retries. The first step in DNS troubleshooting is checking server reachability. Use ping or tracer route to test whether the client can reach the DNS server listed in its configuration. If the server responds, try using nslookup or dig to test specific queries. These tools allow you to submit manual name resolution requests and see how the server responds. This is useful for verifying the presence of a DNS response, checking response time, or isolating whether the problem lies in the server or the client configuration. If no response is received, a firewall or routing issue may be blocking DNS traffic, typically over UDP port 53. Misconfiguration is another frequent cause of DNS failure. This includes having the wrong DNS server listed, often because of an incorrect DHCP setting or manual entry on the client. Even a single typo in the DNS IP address can leave a system isolated from the outside world. Another issue is the absence of a search domain or suffix. If internal names require a fully qualified domain name, FQDN, but users only enter short names, the absence of a domain suffix can cause resolution to fail. DHCP option 15 is commonly used to assign the domain suffix automatically. Split horizon DNS adds another layer of complexity. In environments with both internal and external DNS views, queries may return different results depending on where they originate. For example, an internal system might resolve portal.com/.com to an internal IP, while an external system gets a public IP. If the internal DNS server is unavailable, or if a client is connected over VPN and the DNS traffic is incorrectly routed, resolution can fail. Hybrid environments, where some services are in the cloud and others on premises, are particularly prone to these inconsistencies. DNS caching can also complicate troubleshooting. When a record is cached on the client or local resolver, it may persist even after the authoritative record has changed. This causes systems to reference outdated or incorrect information, leading to failed connections. Flushing the DNS cache on a client using ipconfig/flush DNS on Windows or sudo system d+resolve controls on /destroy forces the system to fetch a fresh record. Also consider the record's TTL, time to live value, which determines how long a cached response remains valid. TTL values too long can delay propagation of changes. Understanding the difference between recursive and authoritative DNS servers also helps in diagnostics. Recursive servers handle the full query process, starting with the root, then top-level domains, then authoritative servers. Authoritative servers are responsible for the definitive answers for their domain zones. If an authoritative server is unreachable, recursive lookups will fail. Tools like dig with the plus trace option can help show where in the process the query breaks. This is particularly useful when troubleshooting domain-wide outages or DNS delegation problems. Switching focus to time synchronization, NTP plays a vital role in system integrity. It synchronizes clocks across devices, ensuring that log files are time-stamped correctly, certificates are validated accurately, and authentication mechanisms that rely on time-sensitive tokens function properly. NTP uses UDP port 123 and is often overlooked until problems arise. But when time drift occurs, it can have widespread effects, from failed domain logins to security logs that can't be correlated across systems. Symptoms of NTP failure include inconsistent or incorrect timestamps on logs, devices rejecting authentication requests due to expired tokens, and SSL certificate errors that claim the certificate isn't valid yet or has already expired. These symptoms often appear as application errors, but the underlying cause is that system clocks are out of sync by minutes or hours. Drift is especially common on virtual machines or isolated systems that miss time updates due to connectivity or configuration issues. To verify NTP operation, use tools like ntpq on Linux or show NTP associations on network devices. These commands display current time sources, synchronization status, and offset values. Compare the system's time against a known accurate source, such as a public NTP server or your own wristwatch. If the offset is too high, the system may not trust the time source and may refuse to update. Also confirm that firewalls are allowing outbound UDP port 123, which NTP uses. Block ports can prevent time updates silently, leaving devices slowly drifting out of sync. For more cybersecurity content and books, please check out cyberauthor.me. Also, there are other podcasts on cybersecurity and more at baremetalcyber.com. NTP issues often come down to configuration mismatches, firewall restrictions, or unreachable time sources. One of the best ways to identify time drift is by comparing device timestamps to syslog messages or logs from known good sources. For example, if logs from a router, a server, and a domain controller show wildly different timestamps for the same event, you've likely found a time sync issue. This can affect event correlation, audit trail accuracy, and even security tools that rely on precise sequencing of events, such as intrusion detection systems and SIEM platforms. Many environments use public NTP servers for time synchronization. Sites like poolntpf.org provide distributed, reliable NTP sources. Large ISPs and government agencies also maintain public NTP infrastructure. However, using external time sources introduces a dependency on internet availability and opens the door to potential misconfiguration if clients are located behind firewalls. Always ensure that your chosen NTP servers are reachable, reliable, and redundant. Avoid configuring external clients to use internal-only NTP servers unless they are designed to support such access. Mismatched configurations can result in silent failures that go unnoticed until authentication or logging fails. Security should also be considered when implementing NTP. Although the protocol is lightweight and straightforward, it is vulnerable to spoofing. If a malicious actor can manipulate time on a system, they can potentially alter logs, bypass time-based access controls, or trigger system errors. Authenticated NTP, though less commonly implemented, is preferred in sensitive environments. Some network devices support NTP authentication using symmetric keys or more advanced certificate models. In addition to enabling authentication, always monitor logs for repeated time sync failures or abnormal offsets. which could indicate malicious interference or upstream errors. In modern hybrid and cloud environments, DNS and NTP challenges are often exacerbated by split architecture. For example, a cloud-based application might rely on DNS from a public resolver, while an internal application uses split horizon DNS that resolves the same domain differently. VPN tunnels may direct DNS or NTP queries incorrectly, leading to failed resolution or broken time sync. Always confirm what DNS and NTP servers are being assigned through VPN connections, DHCP leases, or static configuration on the client. When working with cloud instances or containerized environments, these services might also be abstracted, requiring Cloud NAB diagnostic tools. The Network Plus exam regularly tests DNS and NTP troubleshooting through scenario-based questions. You may be shown a user who can access a resource via IP but not by hostname. The correct diagnosis would be a DNS failure. You might also encounter a system that fails SSL verification despite a valid certificate, indicating time drift. Exam questions may ask you to choose the appropriate tools such as nslookup, dig, or ntpq, or interpret output from one of these utilities. Understanding how to isolate name resolution failures from routing or firewall issues is a key competency. One particularly important point is the dependency between DNS and NTP themselves. DNS queries require IP connectivity, but they also require accurate system time. Certificates used by DNS over ITTPS, DOH, or secure internal DNS servers will fail if the client's time is too far off. Likewise, NTP servers referenced by hostname must be resolved via DNS. If DNS is broken, NTP cannot reach its source. If NTP is broken, secure services relying on timestamp validation may not function. This circular dependency means that when one service is failing, you should always check the other to avoid chasing the wrong root cause. When troubleshooting these services, cross-check dependencies. If name resolution fails, test with both hostman and IP to rule out DNS. If certificate errors appear, check the device clock. Use DNS diagnostic tools to query specific servers and confirm the validity and timeliness of responses. Use NTP verification tools to assess synchronization status, offset, and jitter. If possible, compare with a known good device on the same subnet or VLAN to determine whether the issue is device-specific or network-widely. Most importantly, document which services and tools you've tested to avoid redundant work and keep troubleshooting focused. To summarize, DNS and NTP failures are subtle but far-reaching. When DNS fails, nothing that relies on names works. This includes websites, email servers, domain controllers, and cloud services. When NTP fails, logs become disjointed, SSL certificates throw errors, and authentication systems reject valid requests. The fix often involves correcting a misconfigured setting, restarting a service, or flushing a cache. But identifying the failure requires a deep understanding of how these protocols operate and how they interconnect with other systems. In the field, technicians must be vigilant about verifying name and time settings. A single DNS typo or NTP drift can trigger outages across entire departments. Similarly, in exam settings, recognizing when a system issue actually stems from a name or time configuration can be the key to choosing the correct answer. Practice with the tools DNS lookup, dig, ping, ntpq, trace a route, and know which questions to ask when something breaks. First, start by verifying name resolution, then confirm time synchronization. These simple checks prevent complex troubleshooting paths and get systems back online faster. Thank you for listening to this episode of the Network Plus Prepcast, your trusted audio guide to the CompTIA Network Plus certification. This episode was produced by baremetalcyber.com. For more cybersecurity podcasts, books, and resources, visit baremetalcyber.com. Thanks for joining us for this episode of the Bare Metal Cybersecurity Plus podcast. For more episodes, tools, and study support, visit us at baremetalcyber.com. And before you take the test, make sure to check out the practice questions in the book Achieve CompTIA Security Plus SY0-701 Exam Success by Dr. Jason Edwards. They cover every domain and are a powerful way to lock in your knowledge.